All right, welcome. Today we're going to peel back the very first and, the most fundamental layer of calculus, these twin concepts, limits and continuity. Seriously, this is where the entire journey to understanding change really kicks off. But let's start with a question, just to get our heads in the right space. How do you describe a destination you can get closer and closer and closer to, but you never actually reach it? This little paradox, this idea, it's right at the heart of everything we're talking about today. And that brings us to our first big idea, the art of just approaching a point. It's all about getting infinitely close, right? It's about the journey, not necessarily the arrival. Okay, let's make this super simple. Picture this. You're standing in a room and you decide to walk to the wall on the other side. Simple enough, right? But here's the catch. With every single step you take, you only cover half of the distance that's left. So you take one step, you're halfway there. You take another, now you're 3/4 of the way. You get closer and closer and closer. But if you think about it mathematically, you never technically touch that wall. So this idea, this concept of getting arbitrarily close to something, but never quite getting there, it's a really powerful one. But for calculus to actually be built, mathematicians needed a solid, rigorous way to talk about this. They needed a formal tool. And that's where the limit comes in. That's the tool. It's basically the fancy name we give to this whole idea of getting infinitely close. At its core, the concept is actually pretty intuitive. All the limit is really telling us is that as our input, our x value, gets super, super close to some number, then the output of our function gets super, super close to some other number. See? We're just describing what the function is doing near a point, not necessarily at the point. Now, the formal definition, the really mathy one, kind of visualizes this as a game of trapping. So look here, you see that horizontal band? Let's call that our target zone. Now, to prove a limit exists, we have to show that for any target zone you pick, it doesn't matter how tiny and narrow you make it, I can always find a vertical band around our input point that guarantees my function lands right inside your target zone. If I can always win that game, no matter how hard you make it, the limit is real. Okay, so that makes a lot of sense for a nice smooth curve, right? But what happens in the trickier situations? What if a function has a gap or a hole right at the exact spot we want to look? And this is where limits just show their true power. So take a look at this function. Right at x equals 3, there's this little hole. The function just isn't defined there. We can't plug in 3. But, and this is the key, the limit doesn't care what happens at 3. It only cares about what's happening infinitely close to 3. And as we creep in from the left side or from the right side, it's totally clear that the function is heading for one single destination, the value 5. So here's the crucial point, the thing you have to remember. The limit can exist even if the point doesn't. The limit is the intended destination, even if that destination is just a missing chunk of the road. That's a huge distinction. Okay, so now let's flip the script and look at a different case. Here, as our x value gets closer and closer to 0 from either side, what happens? The function doesn't head towards some nice, neat number. Nope, it just shoots straight up, totally uncontrollably, towards infinity. It never settles down near one spot. And this just brilliantly illustrates the other possibility. If a function doesn't approach a single finite value, we just say the limit does not exist. Simple as that. There is no destination. This whole idea of a destination leads us right into our next big concept, continuity. So while a limit tells us where a function is headed, continuity is all about asking, is the path to get there perfectly smooth? So that leads to the next logical question, right? We know where the function is headed thanks to the limit, but is the actual point on the graph where it's supposed to be? Is that path totally unbroken? Well, to answer that, we have this really simple 3-point checklist. For a function to be perfectly smooth or continuous at a point, 3 things have to be true. First, the point itself has to actually exist on the graph. You have to be able to plug in the number. Second, the limit at that point has to exist. It has to be heading towards a specific destination. And third, and this is the kicker, they have to agree. The actual point's value has to be the exact same as the limit's value. The location has to match the destination. Now, what happens when a function fails any part of that test? Well, that's when we get what's called a discontinuity. So let's take a quick look at the different ways a function can fail this little test. Okay, there are basically 3 main types. First, you've got a removable discontinuity. That's just a tiny little hole in the graph. The limit exists, the destination is there, but the point itself is either missing or maybe it's in the wrong spot. Then you have a jump discontinuity. This is like a broken bridge. The function comes in from the left, heading to one value, and comes in from the right, heading to a completely different value. And finally, there's the infinite discontinuity. That's that vertical asymptote we saw earlier, where the function just flies off to infinity. So, we've talked about approaching points, we've talked about arriving at them, we've talked about broken paths. So what? Why is all of this so incredibly critical? What's the big picture here? Well, it matters because these two ideas, limits and continuity, they are the absolute bedrock of calculus. Seriously, they are the logical foundation that everything else, and I mean everything else, is built on. And what are they building towards? They allow us to define one of the most profound, most powerful ideas in all of science, the concept of instantaneous rate of change. You've probably heard of it as the derivative. Limits let us ask the amazing question: how fast is this thing changing right now at this very single instant? And that leaves us with one final thought to chew on. By understanding how to get infinitely close to a point, we suddenly unlock this incredible ability to see how things change in a single frozen moment in time. So, what secrets of motion, of growth, of the universe itself can we uncover with that kind of power?